The company that sells this product says that the hydrogen peroxide solution is 3%, but when we do our investigation, we'll find out if in fact it is. Today's lab is a determination of the percentage concentration of hydrogen peroxide. Hydrogen peroxide is a substance commonly available in most homes and stores in the US. It is used to treat things like minor cuts and bruises due to its germ-killing abilities. Hydrogen peroxide, or H2O2, undergoes decomposition in the presence of light, enzymes, or certain metal ions. In this process, H2O2 is broken down into water and oxygen gas. The enzyme catalase can be found in nearly all living organisms. Catalase hastens the decomposition of hydrogen peroxide. This video shows the difference in the rate of decomposition of hydrogen peroxide in the presence of catalase found in a piece of potato and without. The slice of the potato on the left has been cooked, which denatures or degrades the enzyme so that it is no longer functioning. The slice on the right shows the decomposition of H2O2 in the presence of catalase in a potato that has not been cooked. Yet even without a catalyst, hydrogen peroxide decomposes because it is thermodynamically unstable. The most common drugstore concentration of hydrogen peroxide is 3%. Because of decomposition, this concentration decreases over time. Sometimes hydrogen peroxide is stored in accordion bottles, which can expand as oxygen is produced. This gives us some idea how much decomposition has occurred in the bottle. Otherwise, we would have no immediate way of knowing. So can we really be sure that the concentration of any bottle of hydrogen peroxide is really what it says on the bottle? Well, in fact, it is likely that the concentration is actually less than what it says on the label. This will be especially true if the bottle has been sitting on the shelf for a relatively long time. The purpose of this exercise is to determine the percent concentration mass to volume of hydrogen peroxide in this product, and we'll do so by titration. A titration is an analytical technique often used to determine the concentrations of solutions. In a titration, a measured amount of a solution of known concentration, the titrant, is added in a slow and controlled manner to a measured amount of another solution whose concentration is unknown. So in this case, our titrant is a solution of 0.0757 molar potassium permanganate, and our analyte is our solution of hydrogen peroxide. The addition of the titrant to the analyte stops once the endpoint of the titration is reached, which is usually signaled by a color change of some sort. In our titration, we will add a certain amount of a solution of 0.0757 molar potassium permanganate to a solution of hydrogen peroxide of unknown concentration. The permanganate ions will react with hydrogen peroxide to produce manganese 2+ ions. All redox reactions consist of simultaneous oxidation and reduction reactions shown below. These reactions show the oxidation of hydrogen peroxide and the reduction of permanganate. Because the permanganate and manganese 2+ ions have different colors, the endpoint of the titration is signaled by the appearance of a pink solution. So here's our redox titration setup. We will fill a burette with our solution of potassium permanganate. The concentration is 0.0757 molar. And we will add it to our solution of hydrogen peroxide that will be placed in an Erlenmeyer flask. We'll continue adding the potassium permanganate solution until the solution turns pink, in which case the endpoint of the titration has been reached. So to give you an idea of the types of calculations you'll need to do, here's a sample problem. Suppose 9.32 milliliters of 0.0757 molar potassium permanganate are required to titrate 2 milliliters of H2O2 to the endpoint. So the first thing we need to remember is that the molarity of any solution is equal to the number of moles of solute divided by the number of liters of solution. We've standardized the potassium permanganate solution concentration as 0.0757 molar. That has not been shown in the video in the interest of time. So utilizing the volume of the potassium permanganate solution, we can calculate, using the stoichiometric relationships between peroxide and permanganate, we can calculate the number of grams of hydrogen peroxide that will have reacted. The calculation of the percentage of hydrogen peroxide is as follows. We take the mass of the hydrogen peroxide solution and we divide it by the total volume, in this case 2 milliliters, and we multiply it by 100. This calculation yields a percentage of 3%. Utilizing the information from the data table, we will calculate the concentration of hydrogen peroxide in this bottle of McKesson hydrogen peroxide. Okay, so at this point I've added 2 milliliters of the hydrogen peroxide solution to 10 milliliters of the 3 molar sulfuric acid. I've read the initial burette reading at 12.40 ml, and at this point I'm going to titrate my solution until the faint appearance of pink as before. Note that the color appears and then it fades as before. When it seems to persist a little bit longer, I will slow down my titration. Going slow pretty much anyway. Let me speed it up a little bit maybe. Okay, I'm starting to get close. Okay, I think I'm there. So I'm going to read the burette again, and it looks to be about, let me read that again, 18.50. The initial burette reading is 12.40 milliliters. The final burette reading of our potassium permanganate solution was 18.50 milliliters. Again, the volume of McKesson hydrogen peroxide was 2 milliliters, and performing calculations similar to the ones seen in this video will yield the concentration of hydrogen peroxide in our solution.